This wire brings power. You still need this one for anything to work, and this one is there to protect you. In this video, I'll show you, in the simplest possible way, how electrical wiring in a home actually works, what live, neutral and ground do, how electricity flows, and why you normally need at least 2 wires for anything to work. And no matter where you live, the basic principle is the same. Whether your house uses 120 or 230 volts, single phase, split phase or 3-phase power, once we pass the breaker panel, electricity works pretty much the same everywhere. So if a house wiring always seems confusing, this should make it a lot easier to understand. And we start with basics. Alright, let's start with the most basic electrical circuit possible. A battery, a light bulb and 2 wires. Can't get more simple than that. The battery is our source of energy, the bulb is the load, the thing using that energy, and 2 wires connect them together. This battery says 9 volts. Voltage is simply a difference in electrical potential between these two sides, plus and minus. A good way to imagine it is like a height difference. Water only flows if there is a difference in height, and electrical current only flows if there is a difference in electrical potential, voltage. Now I've connected these 2 wires to the battery. Now they're basically extensions of the battery terminals, plus and minus. But even though voltage is already present at the ends of these wires, the current doesn't flow yet, because the circuit is still open. Current needs a complete path, a full loop, to flow. If I connect only 1 wire to the bulb, still nothing happens. There is no way for the current to return. But once I connect both sides, we now have a closed circuit, a complete loop, and current can flow through the bulb back to the battery. And that's one of the most important things to understand in electrical wiring. Current needs a complete loop to flow. Now let's apply that same principle to household wiring. Instead of a battery, our power source is now the electrical grid, and the voltage is 230 volts since we're in Europe. Since that voltage is much higher than on the battery we used, it's much more dangerous, so you never touch any exposed metal, any copper, any equipment with your bare hands, and when you work on something you always turn the power off. And instead of plus and minus, we now have live and neutral. This miniature breaker panel represents the point where power enters your home, and where we can switch it on or off. So for this demonstration we can treat it as our source. And just like before, we still need a complete circuit. If either one is disconnected, current cannot flow and nothing works. The main difference is that household electricity uses alternating current, AC, instead of direct current, or DC from the battery. With a battery, current flows in only one direction, but with AC, the direction constantly reverses 50 or 60 times per second depending on the country. Here is 50. It changes its direction because the voltage changes its polarity. The live changes between plus 230 and minus 230, and the neutral stays at 0. So then the current also changes its direction. In one fraction of a second it goes like this, and another one goes like this. So instead of staying permanently positive and negative like a battery, the voltage on the live wire continuously alternates between positive and negative relative to neutral. But even though the direction keeps changing, the principle is still exactly the same. Current needs a complete path back to the source. Even though the direction reverses, we still say that current flows from a higher to a lower potential. So later in the video, for simplicity, I'll be saying that the current flows from live to neutral. So simply speaking, live and neutral together are the household version of the battery terminals or battery wires we used earlier. And once you understand that, real household wiring becomes much easier to understand too. Because a house wiring is really just a collection of these same circuits repeated over and over again. Here's one for the lights, and here's one for the outlets. So what about the earth wire or ground? Unlike live and neutral, the earth wire is not normally part of the working circuit. Most electrical devices can normally operate without it. Here I'll disconnect it. And the light still works. Its job is safety. The earth wire is connected to exposed metal parts, like a metal casing of a washing machine, water heater, or light in our case. Alright, I'll connect the earth wire back. Now this metal is connected to the earth wire. The earth wire from there is connected to neutral, somewhere upstream, somewhere closer to the source, to the transformer. It can be connected inside the breaker panel. I'll open the breaker panel and show you. So this bus bar is where all the earth wires from your house wiring are connected to, and this can be connected to neutral, but before circuit breakers. In that case, you wouldn't need this thick earth wire going anywhere further. Or it could be connected just before the meter. This box represents our meter. So the earth wire will be connected to neutral just here and wouldn't go any further. Or it could go all the way to the transformer and be connected to the neutral there. What matters is that this creates a direct path back to the source. So now if a live wire accidentally touches this metal because maybe these thin wires are damaged, the current can return through the earth wire to the neutral and back to the source, to the transformer. And because this path has much lower resistance, the fault current will be extremely high and it will trip the circuit breaker instantly. If the earth wire is not connected to the metal housing and a live wire accidentally touches it, nothing may happen at first until you touch the metal yourself. And if you're standing on a wet floor or outside barefoot or wearing poor footwear, now this fault current can travel through you, through the soil and back to neutral at the transformer side, because neutral at the transformer side is connected to the soil, to the ground. Now, because both your body and the soil have much higher resistance than a copper wire, this fault current will not be high enough to trip the circuit breaker, but it may be high enough to stop your heart, so this is a very dangerous situation. Now, in some countries, like here in France, another type of grounding system is common. Instead of being connected directly to neutral, the ground wire is connected to a ground rod just outside your house, so it's connected to the soil. From there, the fault current can travel through the soil itself to the transformer, where you have another ground rod which is connected to neutral. But because soil is a lot less conductive than copper wire, the fault current may be too low to trip the circuit breaker. That's why these systems rely heavily on another device called an RCD, or GFCI in North America. It's the same thing, different name. Unlike a circuit breaker, an RCD constantly compares current going out through live with the current returning back to neutral. If there's any difference, it trips. It doesn't matter if a device is connected or not, because if it's not connected, the current in both live and neutral is zero. And if it's connected, the current in both live and neutral should be equal, because what comes out must go back. So if a current starts leaking somewhere else, through an earth or through a person, an RCD quickly detects that imbalance and disconnects the power. And that's what keeps the system safe in the background. Grounding, circuit breakers and RCDs all work together, each with a different role. And once you see how all of it fits together, household wiring becomes much easier to understand. Because everything in your house is just these same circuits with live, neutral and ground, repeated and distributed in different ways. Live brings power, neutral provides return path back to the source, and ground provides a reserve return path if something goes wrong. Lights are connected through switch circuits where the switch simply opens or closes path for current. And outlets or sockets are simply connection points where you can plug things in and complete the circuit. But underneath all of it, whether it's a light, a socket or an appliance, the principle is always the same. A voltage creates potential for current to flow, but current only flows if there is a complete path back to the source. I hope this video helped you to understand how household wiring and electricity in general works. These are just basics, many more things to come. So if you feel like it, if this interests you, subscribe if you want, and see you in the next one.